Okay, guys, more on the normal model. And we're going to get into some really cool stuff here. Um, First of all, let's just take a look at a distribution. It turns out that gestation periods for adults follow approximately a normal model of 266 days mean with 16 days standard deviation. So from this information and the previous video, we know that we can draw, first of all, let's read from left to right. We know we have a normal distribution. We know smack dab in the center of that distribution is the mean. And with this notation, the mean is the first number that we're given. We know the standard deviation, again, is what? Bending, 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 bending. Okay, we start to get a straight line about right there. It's straight, 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 starts to bend. So we want to come about to the center of where it's straight. Make a point. Drop that point down to the horizontal axis. That distance right there is the length of the standard deviation, so 16. So 266 plus 16 is 282. Come across, because bell-shaped, normal distributions are symmetric. Subtract 16. Now I've got this distance, so let's come up approximately that. Add another 16. And add another 16. Come down, subtract a 16. And subtract another 16. So these are all in days. So from the previous video, we know that approximately 68% of gestation periods last between 250 and 282 days. Approximately 95% fall from 234 days to 298 days. Almost all, 99.7%, fall from 218 days to 314 days. It is rare. Only 0.15% of gestation periods last less than 218 days. And it is also rare. Only 15 out of every 10,000 last 314 days or more. Now, guys, it's really important for us in making this connection between samples and populations to bring in the idea of probability. Now, guys, this is not a class in probability. It's a class in statistics. But statistics uses probability to make very, very, very important decisions. In fact, we're going to get into something called a p-value later on in this semester. Going to be a very key ingredient, key component of hypothesis testing that we're going to use to make decisions. So to get the ball rolling in that direction, I want to talk to you a little bit about probability. Probability is some really, really, really neat stuff. And we don't really have the time in this class to give it its due. I mean, there are people, Dr. Whitaker and Dr. Lee at Shawnee State University have PhDs in probability. So we use probability in statistics, but statistics isn't probability. That's a completely different branch. But the best way to think about probability is it starts with randomness. Randomness just tells me that every single possibility has an equal chance of being selected. So a lot of times people misuse probability. For example, they go to a horse race. And let's say there are 6 horses running in the race. And they say, okay, what's the probability that the 4th horse wins? Well, guys, probability isn't appropriate. Probability doesn't apply to the horse that wins the horse race unless we're determining the winner by putting these 6 numbers in a hat and randomly pulling out the winner. Now, if that's the case, then probability applies. But we know in a horse race that probability doesn't apply because the horses race and there's a jockey that rides the horses and there's all sorts of positioning and things like that. So horse racing does not apply. What about grades in a class? Let's say we only have 5 grades, A, B, C, D, F. Well, what's the probability you get an A in this class? Does not apply. The only way that would apply is if I put a slip of paper with an A in a hat, slip of paper with a B in a hat, C in a hat, D in a hat, and an E and an F in a hat. Not an E, we can't do an E, can we? And I randomly pull out your grade and say, oh, wow, John got an A because this A is on the slip of paper. That's not the way we do grades. Grades are hopefully a reflection on learning, right? So again, probability does not apply. What if we roll a die? 6-sided die. 1, 2, 3, 4, 5, 6. What's the probability we get a 6? Well, we have randomness, don't we? We threw the die, assuming that there's no one sabotaged our dice and or the surface that we're rolling it on. Then we would have a random outcome, like flipping a coin. Flip a coin, what are we going to get? Well, we're going to get either a head or a tail. So we have a 0.5 probability of getting a head, a 0.5 probability of getting a tail. We have a 1/6 probability of getting a 1, a 1/6 probability of getting a 2, 1/6 probability, and so on and so forth. Guys, at the end of the day, you can typically let X equal some event. The probability of getting X is going to be the number of successes over the total number of trials, possible outcomes. So the probability of getting a head, there's one way to get a head, there's 2 possible outcomes. So the probability would be 1/2. What's the probability of getting a 6? There's one way of getting a 6. There's 6 possible outcomes. So the probability of getting a 6 would be 1/6. Now, guys, I wish I love probability. In fact, I used to go to Las Vegas a lot, and I love to play blackjack. And I wish I had time to get into this more. But we just use probability as a tool. Well, trust me, I can spell probability. I was distracted. We use probability as a tool to make decisions in statistics. In fact, we teach a probability class at Shawnee, and so it might be something you want to put on your agenda to actually take a class in the area of probability. All right, gang. How does this come full circle to normal distributions? Well, let's go back to the drawing of gestation periods. And let's say we want to find the probability that a particular gestation period is greater than or equal to 282. All right, so what I'm going to do is I'm going to come over here and I'm going to focus on this 282. I know that I have 100% of the area below the curve. So I want to find the area to the right of 282. And it would make sense to me that if everything is random, that the proportion of area under this curve to the area under the total curve would give me my probability. For example, let's say I'm playing darts and I have a square dartboard and it's divided into 4 equal pieces. And again, guys, think random. I'm not talking about a good dart player. I'm talking about somebody's blindfolded and they're going to hit in this area. Well, what's the probability that they would hit, if they're throwing randomly, what's the probability that they would hit in that bottom right-hand square? Well, it'd be 1/4, wouldn't it? Because that area is 1/4 of the total area. So apply kind of the same fundamental, same principle, if you will, to this. If I can find the area under the curve here in relation to the whole area, I can get the probability. Well, what do I know? I know that, first of all, from here back has to be 50%. I know that 68 could be divided to 34 here and 34 there, right? Again, because of symmetry. So I know in this segment right here, I've got 34% of the area, so 34 plus the 50 that goes all the way down to negative infinity gives me 84, so this part up here has to be 100 minus 84, which is 16. So then I would have 16% out of the total 100% gives me a probability of approximately 0.16. What's the probability that the gestation period would be from 266 up to 282? Well, that tells me that I need to concentrate on this area, right? And that area we know from the previous drawing was 0.34. So I have 34% out of the total 100%. So the probability would be 0.34 that we would randomly select a woman who is pregnant and her gestation period lasts between 266 and 282. Now, what if I want to focus on a gestation period of 248? And I want to find the probability that I get a gestation period. I randomly select a woman. Again, probability, random. Okay, so I randomly select a woman, and I want to determine the probability that her gestation period is less than or equal to 248. Well, guys, this drawing's been pretty helpful, but because I'm drawing this, I'm focusing on this gestation period that falls between the two lines defined by the empirical rule, the 68, 95, 99.7% rule. I need something else, don't I? And that something else is I need technology. Now, we could use calculus and determine the answer. Exactly. We need technology. And what we're going to use a really cool function in Stack Crunch to work these particular types of problems. So guys, that's what's coming up in the next video. So what have I hopefully what have you learned in this video? Well, guys, when we talk about probability, you must focus on randomness. Phenomena that don't deal with randomness aren't appropriate for probability. And you see people misuse that all the time. If you roll a die, well, we got a random event. Flip a coin, we got a random event. Choose a lady at random, we have a random event. and we can determine the probability that if we get particular measurements above or below or even between certain values. So that's all in this video. Next video is going to get it's going to get more challenging. So take care.